back to the second half of our lecture about probability, proportions, and standard distributions. As a reminder, we just talked a little bit about the binomial distribution. We've discussed how it approximates a normal distribution, and then we've talked about how we use inferential statistics and probability together to determine if a treatment effect exists. Now we're going to go on to something that I actually think is very fascinating, called the sampling distribution of the mean. But before we get there, we have to remind ourselves of a couple things. So in our last lecture, we briefly discussed, that whenever a score is selected from a population, we should be able to compute a z-score that describes exactly where that score is located in a distribution. And then if the population is normal, we should also be able to determine the probability for obtaining any individual score. Then we talked a little bit about, or we haven't talked about this, but I will establish for you that the z-scores and probabilities that we've talked about so far, we've mostly just been using z-scores to transform raw scores from a population or a sample. But in a lot of research situations, more often we are going to use the sample mean, not actually just a raw score from the sample, to tell us about the population that it comes from. I think that, sorry, my Zoom just popped something up. So yes, the sample mean is often a much more representative value than just any raw score from the sample in determining information about the population. The problem with that is that sample means or samples are variable. So what that means is the mean from one sample of a population is not going to be the same as the mean from a second score from that population. Excuse me. So the way of changing that is that we transform our sample means into z-scores, and then it can describe how any specific sample is related to any other possible sample from that population. And we can determine the probability of obtaining a specific sample from any population, no matter how many scores that sample contains. Do that every time. This is just another example of sampling error, or how all samples are variable. Excuse me. These random samples are all coming from the same population, the population that has a mean of 30.8 and a standard deviation of 7.8. The samples are not just different from the population, but the statistics are actually variable among themselves as well. You can see that the sample means are all different, none of them the same as the population mean. Same thing for the sample standard deviations, all different from each other and different from the population standard deviation, even though all of these random samples came from the same population. So how we correct for that is we create something. Let me make this smaller so you can see my screen. You create something called the sampling distribution of the mean. It's a mouthful, but it's a very cool concept. The sampling distribution of the mean, shown here, is a collection of sample means for all possible random samples of a particular size n that can be obtained from a population. So basically, you take every single possible sample that you could take from a population, you determine the mean of every single one of those samples, and then you graph those means, and you get this, called the sampling distribution of the mean. The characteristics of the sampling distribution of the mean are as follows. The sample mean, so the sample means, everything we're graphing here, are going to pile up in a normal-ish distribution around the population mean, with a tendency, like we said, to form a normal distribution. The larger the sample size we use, the closer the individual means that we're graphing here from the samples should be to the population mean. So as the sample size increases, these means will get closer and closer to the population mean from which they came. And the last characteristic is that the mean of all the group means will be the same as the mean of the population. So that's kind of confusing, but let's say it in a different way. The mean of this distribution, which is a collection of the mean from every single sample. So the mean of the means is going to be the exact same as the mean of the population from which those samples were drawn. Okay. Oops, I always says that. The central limit theorem is a theorem that has been proposed and validated to describe the standard distribution of the mean. And it states that for any population that has a mean and a standard deviation, the distribution of sample means, so that distribution we were just looking at, for a sample size of n, will have a mean that is the same as the one from the population and a standard deviation that is the standard deviation of the population over the square root of the sample size. And it will approach a normal distribution n, or a normal distribution as the sample size approaches infinity. Basically, this doesn't tell us anything new. It's just restating what we said in the last slide. But the important thing here is that the sampling distribution of the means, that distribution of the sample means that we were just talking about, approaches a normal distribution as the sample size gets larger. There are two important things here. This theorem is going to hold true for any distribution of sample means for any population, no matter what the shape, the mean, or the standard deviation of that population was. So even if the population was like positively skewed, this central limit theorem would still hold true. And the sampling distribution would still be normal. And then two, the distribution of sample means is going to approach that normal distribution very rapidly, very, very quickly, as you add more sample means to it. So the central limit theorem is going to describe the distribution of sample means by identifying three basic characteristics that describe any of them: the shape, the central tendency, and the variability. So let's talk about that. So the shape of the sampling distribution of the mean is almost perfectly normal if either of these two conditions are satisfied. So number one, if the population from which the samples were selected is a normal distribution, then obviously the shape of the sampling distribution will also be normal. But even if the shape of the population distribution is not normal, even if it was like positively skewed, if the number of scores in each sample is around 30 or more, then the sampling distribution will still approach normal. So that's about the shape. The central limit theorem talks about the central tendency of that as well. And we've already kind of talked about this. The mean of the sampling distribution of the mean of that distribution we talked about, is always identical to the population mean, which we already just talked about. We established that on the last slide. This is what we call an unbiased statistic. So on average, the sample statistic that we're getting, the mean of this sample, is going to produce a value that is exactly equal to the corresponding population parameter, the mean of the population, which is very, very cool. In other words, the average value of all the sample means is exactly equal to the population mean from which it came. Now, let's talk a little bit about variability. The variability of the sampling distribution of the mean has a special name. It's called the standard error of the mean. And it tells us more than just about more than just the standard deviation, but we'll discuss that in a second. The standard error of the mean is, by definition, the standard deviation of the sampling distribution of the mean. Basically, this is just going to describe the distribution of the sample means. It gives us a measure of how much distance is expected on average between a sample mean and the population mean. Here is the formula for that, and we'll come back to this in a second when we're talking about some characteristics, when we're talking about some characteristics of the standard error of the mean. The first bullet point here says, that the standard deviation for the sampling distribution, the standard error, is going to be less than the standard deviation of the population. This makes sense, right? Because individuals from a population are going to have way more variation than groups from that population. The groups are going to be more similar in general. The samples are going to be more similar than the individuals by themselves. So the population standard deviation will always be more than the standard error of the mean. The second bullet says, as the standard deviation of the population increases, the standard deviation for the sampling distribution will also increase. And that makes sense too. Basically, we're saying for any given sample size, the more the individuals in the population vary, the more the groups, the samples will vary as well. This third bullet says that the law of large numbers tells us that the larger the sample size, the more probable it is that the sample mean will be close to the population mean. Basically, as the sample size increase, the sample means are going to get closer and closer and closer to the population mean. Because larger sample means are going to be clustered more closely together than smaller sample means. And then this last one says, basically, what we just established, that as sample size increases, the standard deviation for the sampling distribution, the standard error, is also going to decrease. So as a summary of all of these things, the magnitude of this sampling error is going to be determined by two factors, both of which are shown in this formula. Number one, the size of the sample, and we've already established this, that as the sample size increases, it's going to be more likely that the sample standard deviation is going to, or the sample mean is going to be closer to the population mean. So standard error decreases. And then the standard deviation of the population also affects it. As the standard deviation of the population increases, the standard error of the mean will also increase. This is just a graph that shows the relationship between the sample size and the standard error. Like we said before, as the sample size increases, there's going to be less error between the sample mean and the population mean, which means that standard error, which measures this, is going to decrease. And it decreases very quickly. Exponentially, one would say. So let's put kind of all of these topics together and talk about the probability of samples. So a z-score, like we said before, or actually, let's go back to this in a second. The primary use of the sampling distribution of the mean is going to be to find the probability that is associated with getting a specific sample from any given population. And we can use z-scores to find the location of one group or one sample with respect to all of the other samples of the same size from that same population. I have hiccups right now. Oh my goodness. Oh. Okay. This is the formula with which we transform. Excuse me. I'm going to take a second to get a drink of water before we continue. Sorry about that. Like we said before, we can use z-scores and proportions to figure out how representative your sample is of the population based on how similar the mean of your sample is to the mean of the population. We do that by calculating z-scores using this formula. And this is an important note. Whenever we're working with the sampling distribution of the mean, we need to use the standard error as the denominator instead of the standard deviation. And we'll talk about this process a little bit later. So a little bit more on the applications of standard error outside of just calculating z-scores. So the general concept of sampling error, which is different than standard error, sampling error is the idea that a typical sample is not going to give you a perfectly accurate representation of the population from which it comes, right? That there's going to be some error between the sample statistic and its corresponding population parameter. And that totally exists in the standard distribution of the mean as well. What we have found is that individual sample means from a population are not going to exactly equal the population mean. 50% of the samples that you draw are going to have means that underestimate the true population mean, and 50% of your samples from any given population are going to have means that overestimate the true population mean. Oops. Thus, the standard error is going to give us a pretty good method for defining and measuring sampling error, because it's going to tell us how far away our sample mean is from the population mean, which is a very important statistic for us to know. The majority of sample means are going to be relatively close to our population mean. They're going to give a pretty good representation of the population. But there are some samples that produce means that are out in these tails of the distribution relatively far, and they don't accurately represent the population. So we as researchers want to know, are our means out in the tails, very far away from the actual population mean, or are they in the middle here and are a good representation of the population mean? And standard error, like I said, tells us that. Here is an example before we leave the topic of standard error that here's just a diagram that shows us the effect that sample size has on the standard error. So here are 3 different distributions with different n values, with different sample sizes. This first one has a sample size of 1, so we just have one sample mean represented here. This one has 4 samples, and this one has 100 samples. So as we see that as the sample size increases, our standard error is going to decrease exponentially. With 1, this standard error is 20, which is the same as the standard deviation, which is actually not a good thing. We don't really care about that. All we want is that our standard error here is as small as it can be, because that means that most of the sample means are very, very close to the population mean. Yeah, that's why this is important. Notice that the size of the standard error decreases as our sample size increases. Before we leave this topic, let's talk about some APA guidelines for reporting these results, and then we'll look at how these look reported in the literature. So here's how to report the sampling distribution of the mean and a standard error in a table. Generally, you'll take your sample statistics up here and your population statistics down here, with your mean and your standard error here, the raw score first, and then your z-score that you've translated. Same thing for population, raw score, then z-score. Good note, remember, the mean of your z-score distribution is always going to be 0. Okay, here is an example of how to report those 2 things in a line graph. We can see that the mean of each of our samples is represented here by this middle value, this green line. And then our standard error is reported with these blue bars. Basically, if our mean, let's say, was 34 here for one sample, and our standard error for this sample was like a 4, you will see it in this bar here, because it's 4 above and 4 below the mean. That's how they report standard error. Similar thing for when you're reporting it in a bar graph. This time the top of the bar represents the mean of each individual sample. And then these error bars, again, are going to represent the standard errors. And I missed this on our last slide, but population parameters, so like the sample size, the mean of the population, and the standard deviation of the population, are generally reported in text underneath the figure. And here's how we report some of these descriptive statistics in literature in a paper. Oftentimes you'll see it represented in a table here with your mean and your standard error for each of these samples. Same thing, just in a bar graph here. This is a very common addition to a bar graph in literature. They say, note that the light gray box around the 0, this thing here, indicates 1 standard error of the mean around the control mean. I really, really like this description as well. they go through really specifically how they found each of the statistics, but they didn't say any of them specifically. They just said that domain scores for measures of executive function, attention, and memory were generated by averaging the standardized data from the test, as presented in table 2. They just referenced their figures because they did all the work to put it in a figure anyways. And this shows a very similar thing. They reported it in a table and in a graph, which look very similar to our previous ones. And then they told us where to find it and reported it briefly in their results. Okay, and that is the end of our discussion about probability and proportions. And I will see you for our next lecture where we expound upon some inferential statistics.